All interpretations of quantum mechanics are shaped by the four terms that appear in the question, why does the wave collapse when an observer measures it? In the wake of John Bell's work on inequality in the 1960s, this question proved more difficult than either Bohr or Einstein had hoped, forcing us to ask deeper questions as to what the wave, the collapse, or the observer actually represent, and further, what constitutes measurement. So in this chapter, we'll unfold some of the more mind-bending ways that thinkers have attempted to unravel this conundrum, and depending on what insights can be gleaned from this collective, we'll then turn to see what impact it might have on our series' ongoing search for the boundaries of consciousness. So join me as I attempt to unpick the infinities of what is. Interpretation 1. Consciousness collapses the wave. In 1932, mathematician John von Neumann pointed out that the definable moment at which a particle collapses is entirely arbitrary. In the double-slit experiment, for example, there's simply no reason for us to think that the probability wave collapsed only when impacting upon our detector. Indeed, there is no physical mechanism in quantum mechanics whatsoever that would enable this transition from a chain of probabilistic superpositions to a definite state, be it between the electron ray and the slit and the measuring device and the results appearing on our screen, the screen and our eyes, or even between our eyes and brains, as each element is itself a quantum system that becomes entangled with the whole. So, where can the line be drawn? In 1961, physicist Eugene Wigner proposed his own thought experiment that extended upon Schrödinger's paradox. As with Schrödinger's skeptical experiment where the unobserved cat in a box is said to be in both a superposition of dead and alive, here we are asked to consider what happens to the observer before they are observed. Since we can consider the same event from the observer's friend's perspective, sitting just outside the closed laboratory. From Wigner's friend's vantage, it seems that both observer and cat share this property of undetermined superposition, existing in both the unfortunate state of opening a box with a dead cat inside, or in the equally unfortunate state of opening a box containing a, shall we say, less than amused cat. But when the friend opens the door and asks the colleague how it felt to be in that state of superposition, the observer just stares baffled. No experience of superposition ever befell the observer, just as you or I have never experienced a dual state. Each observer's observation therefore suggests some element of finality. But if all observations are taken to be closed states, and if quantum mechanics is to be considered universally valid, then the notion of a single observer-independent set of facts becomes next to impossible to maintain. What is real is therefore only what is real within observation. In fact, laboratory variations of this very experiment have since been undertaken supporting the idea that observation shapes reality. In their 1939 Theory of Observation paper, Fitz-London and Edmund Bauer stated that, quote, "The heart of the matter is the difficulty of separating the object and the observer," end quote. As the authors saw it, the mind, as the locus of subjective knowledge, had great potential to be the guilty hand at play, since the perpetual mixing of physical superpositions should remain present so long as no information is added into the system. For London and Bauer, this addition of information was the objectivity and introspection of conscious observation. In short, measurement is not complete until it is consciously observed. And so, concerning the double-slit experiment, the waves we see appearing when neither of the two slits are being observed are merely a result of the fundamental mixed state of the system that exists before the addition of knowledge found in conscious intervention. The practical upshot being that when we aren't looking, the moon isn't there. At least, not in any determined state. It's almost as if the moon's intrinsic identity remains embedded within the fluxing wholeness until a conscious measurement re-elevates it into our determined macroscopic plane. Physicist Henry Stapp is another who has argued that the only aspect of the system that can step outside of this entangled physical chain is the consciously determined will of an observer. Stapp argues that each expression of consciousness is, by its very nature, entirely definite, rendering superpositions of conscious states paradoxical, this making it the only definable wall in what would otherwise be an infinite regress. The idea is that if mind states correlate with brain states, then the quantum state of the physical brain must be equally determined, thereby causing the collapse of the entire entangled system. Such a theory, if proven, would potentially solve the hard problem of consciousness and the measurement problem in one fell swoop, though again, it's not without its problems. One being the old adage that a watched kettle never boils, which, in this case, would be literally true. The quantum Zeno effect is a phenomenon in quantum mechanics that shows how continuous measurement prevents a particle from evolving according to the Schrödinger equation. However, in a model that equates measurement with consciousness, continued observation would essentially freeze the evolution of all quantum systems, rendering measuring devices useless and making the process of waking up simply impossible. Further variations have grappled with this problem, offering reasonable workarounds, but inevitably, the advocate, like the advocate of any quantum mechanical interpretation, is left with the burden of finding further evidence. In recent decades, the consciousness collapse theory has been largely abandoned. Philosophical problems concerning the theory's implied dualism, the idea that mind and matter are completely unique properties of the universe, or the simple issue as to what exactly waited around for 13.8 billion years before sufficiently conscious observers appeared, not to mention our own conundrum of how we should best describe a conscious observer, have all proved problematic for the theory. As Professor David Albert puts it, quote, "What this theory predicts will hinge on the precise meaning of the word conscious, and that word simply doesn't have any absolute precise meaning in ordinary language." End quote. But despite the fact that even Winner himself eventually stepped away from the theory, there are still a handful of good reasons to avoid abandoning the idea altogether. At a basic level, as Bohr argued, physics is only an analysis of the phenomena arising from our interactions, with concepts like location, momentum, or spin applying only within the context of the experiment. We select the question, nature selects the answer. But the answer itself only stands relative to our question. And so, as the book has not been fully closed, reinterpretation has clearly been needed. So what if we follow the modern intuition and discount consciousness as the primary catalyst for collapse? What then? Interpretation 2. There is no collapse. Unfortunately, the paradoxical behaviour revealed by the Winner's friend thought experiment doesn't just up and away with the conscious protagonist, since without consciousness closing the loop, every thing, object and system still retains that underlying suggestion of superposition said to exist prior to the measurement. So the line still has to be drawn somewhere. But what are the alternatives? Well, first, we can start by replacing conscious observation with mere physical interaction. What we're then left with is only the wave function of probabilities and this prickly point of collapse. One possible suggestion could be that there is no collapse. After all, the equations never describe anything like a collapse, only the temporal unfolding of the probability equation, i.e. the superposition of probable points in space and time. The addition of collapse is merely an abstraction, forced upon us by the fact that we only ever measure definite states. So, if not a collapse, could we instead be dealing with something more akin to a separation? A branching of each probability, each coming into its own, uniquely and independently, as a self-determined universe amid an infinite sea of universes. I'm sure that, for many of you, this interpretation is egregiously worse, though it's still arguably the second most widely taught interpretation of quantum mechanics today, the many worlds theory. An idea that has worked its way into the modern zeitgeist due to its deliciously science fiction-esque conclusions, now responsible for such inspired works as the Marvel Universe. Or something a tad closer to my heart, the animated series The Midnight Gospel, or the 2022 film Everything, Everywhere, All at Once. So for any movie, book, or series that explores multiverse themes, a small amount of thanks should be given to the theorists' founder, physicist Hugh Everett. Everettians, as they have increasingly come to be known, believe that the many worlds theory solves the measurement problem by doing away with collapse, whilst still retaining those undetermined superpositions. The idea, though often misinterpreted, suggests that upon interaction, a particle becomes entangled with its environment, thereby determining the relational structure between said particle and its environment. From that point onwards, all paths that the electron might have taken are cut off from this relational structure. But we still need to ask what happened to all the other potentialities represented by the superposition before this interaction. The idea is that in all potential locations where the electron may have landed prior to the interaction, it did. The catch is that it did this in a newly branched arm of the one universal wave function. This is where most film interpretations of the many worlds theory mislead their audience, as no new you popped into existence at the point of interaction. That is to say that there was no duplication event. Rather, both future histories are emergent aspects of a prior whole, much like how two species will diverge along evolutionary lines without ever needing for a new species to pop into existence. Instead, we're asked to imagine ourselves as spread out along a complex mathematical structure called Hilbert space, an infinitely multidimensional continuum that is the home of this sole universal wave function. A wave function that doesn't exist within time and space, but rather gives rise to time and space in the form of quasi-classical universes. What would be true is that, functionally speaking, once a specific universe has decohered and stabilized amid the chaotic turbulence of Hilbert space, it can then be considered its own informationally isolated spatio-temporal universe, just as the new species can be considered its own unique branch. But for Everett, we need to remember that there is still only one space-time manifold, be it somewhat pockety. The popular emphasis on separate universes stems from the more explicit DeWitt interpretation of many worlds. It's not incorrect, nor necessarily anything different from Everett's original vision, but the point is that the division, splitting, or multiplication of worlds has more to do with our confused and limited perspective on what we actually are. As we are not a single one whose pattern has seen an infinite series of duplications. Rather, we are only one branch of a greater relative relational structure, emerging from the sole universal wave function, a continuum of relational branches, each stemming from the same trunk. However, there are some confronting implications for a Hilbert space that is seen as an unbroken continuum, as it suggests that every possible branch has a 100% certainty of occurring. This is problematic because it undermines the very thing that the model attempts to retain, i.e., the dynamics of the probability wave. Since if highly probable results are just as likely to occur as those that are less probable, what does it even mean to say that one path is more probable than another? This isn't merely a minor quirk, it is the central unresolved problem of the many worlds interpretation known as the Born rule problem. If all outcomes are equally real, shouldn't the most unlikely of universes be equally possible? Why should my universe be the one that is weighted by the wave function? This is the issue with interpreting the universe mathematically. Though an equation may make sense on paper, the leap from mathematical structures to ontological is at present only a metaphysical statement. Though there is good reason for people to hold this unwavering faith, since historically it has proven a reliable path. Almost all our great theories originated in equations, so why stop now? As Bohr put it, quote, "It is not for us to tell God how to run the world." End quote. The greater issue, as we have come to recognize across the last few chapters, is that the limitations of perspective often mislead us, as any apparent independent appreciation through one set of eyes will, on closer inspection, always reveal itself to be nothing more than an emergent property of something more fundamental, which is why some have begun to pay closer attention to these frames of perspective, hinting that this might indeed be the responsible hand at play. Interpretation 3. Perspective is key. More recent theories, such as cubism or relational quantum mechanics, have sought to identify these limited frames of perspective, doing away with both collapse and the unintuitiveness of many worlds by once again placing a relational perspective at the centre of measurement. However, historically, this has been a difficult feat to achieve without invoking a mystical appreciation of consciousness. RQM, or Relational Quantum Mechanics, as devised by physicist Carlo Rovelli, claims to successfully reframe this problem with only the most meagre of sacrifices: the loss of objective reality itself. Strong realism is a philosophy that holds that there is an objective reality out there waiting to be discovered, and that we will always have the ability to uncover it given enough time and effort. But Rovelli does away with this presumption, suggesting that there is no absolute objective universe out there waiting to be discovered. Instead, every system should be understood purely in relativistic terms, a type of perspectival realism. So that just as there is no universal clock dictating a universal passing of time, nor any ether-like background to measure a universal position or velocity, neither should we consider there to be a determined universal history of objects and events. In RQM, every system is said to host its own meaningful perspective of reality, not a conscious perspective, but a relativistic relationship. As with our philosophical encounter with process, each perspective derives its legitimacy from an appreciation of relationships. And since no system can ever measure itself, universal facts can't exist in a vacuum. But there are some peculiar implications of this, as it suggests that from within unique frames of reference, systems can observe results that differ from those observed by other systems. But for Rovelli, a system is more than just a particle, as the class system includes the experiment, a human observer, or even a simple light post. As with all relativistic thinking, no system can ever claim an absolute perspective on truth. At a fundamental level, systems can now be imagined as little more than a series of binary questions, inherently probabilistic yes-no bits of the universe. For example, Did the particle go through slit A? Regarding the double slit experiment, from the perspective of the measuring device, the which way information is determined as being either slit A or slit B when that information is shared through interaction with the particle. Both systems decohere relative to one another. However, from the perspective of the observer who did not access this interaction, but treated the two independent systems, particle and device, as a single entangled system, the particle appears superpositional. However, once the observer acquires this information through their own observation and measurement, the determined state is incorporated into their perspective, making the results determinable from within that new frame of reference. We see a particle. Ravelli explains that the mind-matter explanation of the world is classical in its nature, and that, quote, reality admits one description per observing system, each being internally consistent. In turn, any given system can be observed by another system, end quote. Meaning that experiments, people, and light posts can operate quite contentedly in the ways we experience, even though no classical objects can ever be totally reduced to the description of a fundamental thing. Fundamentally, these emergent attributes of our perspective can only ever be appreciated as interacting systems of relation. A different relational theory, cubism, takes a similar approach, if not more drastic, rejecting the physical interpretation of quantum mechanics entirely, suggesting that all we experience is subjective. Unlike RQM, where any physical system is taken as a perspective holder, cubism is intentionally vague as to what relational systems include. These are very much agents of experience, but whether or not experience means consciousness depends on the deeper question as to what consciousness is itself. So this isn't to say that reality is purely mental, as per the idealist's view, but only that probability assignments are a factor of subjectivity, not objectivity. The world beyond these subjective probabilities is something far less defined, an implicate order of flux. Christopher Fuchs, one of the leading proponents of cubism, describes quantum mechanics as, quote, a law of thought. The wave function does not describe an aspect of objective reality existing beyond the observer. It describes the observer themselves, end quote. In this way of thinking, Fuchs and his colleagues do away with both the collapse and the idea of probability, suggesting that the wave function is instead a reflection of the agent's ignorance. In respect of the double-slit experiment, the probability represented by the wave equation is a reflection of the observer's degree of belief as to what the measurement might be. The moment of collapse is then reinterpreted as an updating of those beliefs. However, the blatant slap in the face that follows is that these wave functions of belief are personal, and so don't need to be agreed upon by any other observer. A cubist would hold that, in a macroscopic environment, this rarely proves to be an issue because we tend to base our subjective probabilities on the same information. Thus, we are more likely to share an objective reality. In essence, our personal probability assignments align with those of others around us. But though these interpretations give us new ways of looking at the problem, both RQM and cubism, like all other attempts, cannot complete the derivation of quantum mechanics. As quoted in the closing pages of Ravelli's beautifully exoteric book, The Order of Time, quote, in the end, every attempt to impose order leaves something outside of frame. Interpretation 4. Hidden variables. And so, the final interpretation that I wish to walk us through is one that might bookend our discussion, as it seeks to bring back onto the stage the story of hidden variables, like those originally theorized by Einstein in his debates with Bohr at the beginning of the 20th century. But also, not quite. as it is actually something very different. This is the interpretation offered by David Bohm himself, formulated very shortly after the publication of his book Quantum Theory and his subsequent falling out of love with the quantum theories of Bohr. It's a theory often referred to as pilot wave theory, though it can just as commonly be called Bohmian mechanics or de Broglie-Bohm theory. Unknown to Bohm, the idea had already been considered by Louis de Broglie 28 years earlier. Even then, in 1924, the idea was swiftly abandoned, considered simply too incompatible with the working models of the time. First published by Bohm in 1952, this theory, in contrast to our prior list of interpretations, goes so far as to boldly suggest that our particle is indeed, wait for it, objectively real. That it does actually have some determined state of existence, regardless of whether we measure it or not. So could it be that, at our journey's end, we've finally come across a description that allows us to reclaim what we gave up on so long ago, a sense of normality? Is this a place where we might hang our hat and offer our day-to-day intuitions some brief respite? By producing a theory that retreats into the familiarities of realism, as Einstein had hoped, Bohmian mechanics has the rare benefit of completely doing away with a theory of collapse. That said, the theory found its biggest critic in Einstein himself. A friend of Bohm's, he was quoted as referring to the theory as a physical fairy tale for children, a position provoked by the theory's fundamental attributes of non-locality, not of the particle, but of the wave. Not unlike its author, this theory has had a somewhat turbulent life, being largely dismissed for the best part of the 20th century. Though it appears that Bohm's work is now taking a happier turn, as in the desperate attempt to shed any light on this century-long stalemate, graduate students have begun to rediscover Bohm's work, leading to a respectable resurgence of interest and consideration. Perhaps not as a fully fledged answer to the measurement problem, since even Bohm himself chose to recontextualize the whole story under his metaphysical framework later in life, but at very least as one of the few examples of a mathematically consistent theory that can offer objectively real particles, even if it is at the cost of the wave's non-locality. The idea itself is primarily concerned with how particles move, not just when passing through double-slitted barriers, but in general. The theory suggests that an objectively real particle, whilst retaining its own determined location in the universe, will move in accordance with a guiding equation that corresponds with Schrödinger's probability wave. A simplistic and naive reading of this dynamic could be the metaphor of a surfer riding waves upon the ocean, where, like the surfer, the particle rides upon a broader field of rapidly changing chaotic fluctuations, quote, all of which combine to determine the detailed behaviour of each individual system with the passage of time, end quote. However, the wave is not a space-time wave or anything physical. Rather, the entire universe is said to behave like a single, indivisible system, where the motion of each nodal point is determined by the configuration of the whole. Not merely via speed of light interactions, but instantaneously and non-locally, with the motion of any particle depending on the configuration of all particles, even if they aren't entangled, even when separated by galaxies. It's not suggesting faster-than-light communication, only a mathematical structure whose global configuration determines the motion of all its parts, a unified configuration space, not many wave functions, just one. Though in his later Metaphysics, Bohm did speculate about an infinite regress of deepening layers, the quantum mechanical theory discusses only a single layer of hidden variables, the particle's determinable movement in space and time, no more, no less. In respect of the double-slit experiment, this guiding wave equation is thought to be passing through the slits at all times, which is why when the unmeasured particle moves along the experiment, its trajectories will lead to the build-up of the interference pattern. But when measuring the particle, we realize that we do in fact have two very different experiments taking place, the one with the electromagnetic measuring device and the one without, i.e., two different states that the universal wave function could be in. It is thus the universal wave function that is entangled with the detector, not the individual particle nor any local wave of probability. No collapse, just a different universal wave function. Though for myself, it is in the metaphysics that Bohm introduced in Wholeness and the Implicate Order that succeeds best in responding to the questions that lie beneath these systems. As he says, quote, "We have to regard the universe as an undivided and unbroken whole. Division into particles, or into particles and fields, is only a crude abstraction and approximation. Thus, we come to an order that is radically different from that of Galileo and Newton, the order of undivided wholeness." End quote. What's important to stress is that even though we may use spatiotemporal metaphors, we should not think of particles, waves, or any layers of relationality as separate domains. He acknowledges that there still has to be what he calls a maximum degree of determination, being a minimum scale at which observables are still considered meaningful, but the concept of a reality bedrock should be considered flawed. There may be limits to nature's particle-like interactions, or even a limit to what we appreciate as causality, but not an absolute flaw. The argument being that reality may be infinitely divisible, with each perspective of nature enfolded into its next, until we are forced to encounter a scenario where all implicates all. Implicate orders embedded within an unmeasurable and wholly united totality, and explicate orders presented to us in the realm of observables. Clearly, there has been much in these physical stories for us to contemplate. But regardless of whether hidden variables exist or not, whether nature is determined, probabilistic or non-local, the fact remains that across each and every theory, we were never compelled to interpret our limits as metaphysical endpoints. Be that a superposition of unmeasurable indeterminacy, a conscious reactive physicality, a multiverse, or an independent frame of relational perspective, each description always drew its own arbitrary lines around its chosen domain of measurement. And so, ultimately, it remains, as Rovelli put it, that every attempt to impose order always leaves something outside of frame. The speed of light, or the Planck scale, may rightly be understood as the end-of-the-road limits for any discussion concerning matter measured by matter. But regardless of which interpretation we lean into, we're still forced to contemplate some uninterrupted continuation. Neither between any two physical points, nor even between our physical and conscious perspectives, have we ever located the existence of ontologically absolute borders. So I think that here, in light of all that we've now learnt, we should finally readdress our original question as to where the bounds of consciousness really lie. Because whether we consider consciousness as either separate from or embedded within its environment, we must at very least acknowledge that it is, at all times, relating to its environment in some process-relevant way, acting both participatorily and relationally, relating to all that surrounds it and all that fills it, whilst also from within a certain finite perspective can we also appreciate its own degree of independence as the participating agent. For importantly, consciousness has never been a thing. Primarily, it's a relationship. So, in the hope of pushing our search towards more fruitful grounds, we should, in our next chapter, reward our hefty efforts with a merry jaunt in metaphysics. But just before we do, I want to encourage you to use this pause between thoughts as an opportunity for reflection, to give yourself the permission to have the time to ask yourself, what do you think is happening? Good morrow, everyone. I hope that wasn't too big of an episode for you. I hope you enjoyed it. Just wanted to let you know I have started to work on a short course that I'm going to do later this year, which will be highlighting some of the ideas that appear in the Infinite Now book, which has to do with the metaphysics of being and truth and identity. And what I've done is I've just made a small expressions of interest form. You can find that on our YouTube homepage. If you go to our homepage and then click on posts, you'll see that there's a post there that links to the expressions of interest form. And there you can give us a little bit of insight as to what you would like to get out of a course like that and whether you're interested. And make sure that you're on the list when it does finally get finished. But until then, much love, and I hope you all have a wonderful, wonderful month. We'll see you soon. All right, bye.